In order to start discussing our results from our lab, it's important to discuss a little about the background and significance of interferometry and interferometers. Firstly, let's begin with some background where we'll discuss what is interferometry and how does it work, what is an interferometer, why they are useful, and what are some of the different ways an interferometer can be set up. Your first question might be, what is interferometry and what is an interferometer? These are good questions. Firstly, interferometry is a specialized technique where interference patterns of electromagnetic waves are used to measure some attribute of the wave or the medium that it's traveling through. These interference patterns are caused when two wavelengths of light are superimposed, creating either constructive interference when the peaks of the wavelengths align, or destructive interference when the wavelengths are out of alignment. There's a vast amount of applications for interferometry for measuring distance and change in distance to being used as an optical filter to filter out certain wavelengths. The interferometers we will be looking at are optical interferometers. So what is an interferometer then? Well, it looks something like this. This example in particular is a Michelson interferometer, where the light source emits a beam of light that hits a half-silvered mirror, which splits the beam in two. One half of the beam continues through the mirror, while the other is reflected down. They both continue on their path until they each hit a mirror and are reflected back, when they recombine, superimposing on top of one another and forming an interference pattern that can be viewed on a screen or a light detector. All optical interferometers will do this in some form, as they are designed to combine two wavelengths of light and superimpose them on top of one another, causing an interference pattern that can be viewed. Interferometers are used for making precise measurements because they're incredibly sensitive to tiny changes in the components of the setup. This is due to the generally very short wavelengths of light used. Because these wavelengths are so short, only a tiny change in their position is required to create an interference pattern. There are several different ways an optical interferometer can be set up, but we'll just be discussing the two setups we used in our experiments. There are additional elements that can be added to each setup to change what sort of characteristic we're trying to measure. These will be discussed later in the results for the experiments. The first type we use, which we've already discussed, is the Michelson interferometer, where a beam of light is split by a half-silvered mirror and returns to superimpose on top of itself and cause an interference pattern. The second type of interferometer we used is called a Fabry-Perot interferometer. It uses two mirrors set parallel to each other to create a reflective cavity. When the beam enters this cavity, it is split into a single incident ray, resulting in a constant phase relationship. The result is a circular fringe pattern similar to the Michelson interferometer. The fringes, however, are brighter, thinner, and spaced further apart.
Furthermore, it's important to discuss the significance of interferometers and how they have played a vital role in science and engineering. We will discuss an early major use, the measurement of speed of light using an interferometer, and LIGO. The initial use of the Michelson interferometer in 1881 was designed to test the existence of a luminiferous ether. The ether, as they called it, was a hypothetical medium in which light propagated. As there was no conception of self-propagating electromagnetic waves, Michelson experiment is renowned for being one of the most failed experiments, as due in part in his findings, the ether is no longer considered a viable hypothesis. During Michelson's experiment to test the existence of the ether, he attempted to do so by measuring the speed of light propagating in two directions relative to the ether. In the same direction of the ether, the value of the speed of light would be c plus v, and the speed of light traveling against the ether would be c minus v, with c being the speed of light and v being the relative speed of the ether. As there was no change in the final measurement, all that was found was c, which is calculated to be around 298 million meters per second. The value found was only 48 kilometers per second less than the exact value used today. The experiment was so accurate in determining a result, it wasn't attempting to ascertain that its value became the standard and most accurate measurement for the next 40 years. While many of the pioneering interferometer uses occurred in the late 19th and early 20th centuries, interferometry still holds a place in the cutting edge of modern physics. A notable example is the Laser Interferometer Gravitational Wave Observatory, or LIGO for short. LIGO uses a setup similar to a conventional Michelson interferometer with one major difference. The two beam paths on LIGO are about 4 kilometers long, And on top of this, the beams travel up and down these arms 280 times, giving a total trip length of around 2,200 kilometers. Given how sensitive the 10 centimeter long paths in our interferometers are, it is easy to see why LIGO can detect a change in a distance less than 1/10,000th of a diameter of a proton. LIGO has detected a number of gravitational waves since 2015 and continues to provide a groundbreaking insight on the workings of the universe.
Now we've discussed some of the background and significance of interferometry, we can go through the 4 experiments conducted in the laboratory. The aims of these 4 experiments were as follows: to measure the wavelength of light emitted by a helium neon laser, to measure the refractive index of air, to measure the refractive index of glass, and to determine the speed of light in air or a vacuum. The first experiment in our lab session was to construct a Michelson interferometer and use it to measure the wavelength of light output by a helium neon laser, which was specified to have an output of 630 nanometers. The pattern of interference we observed changed as the length of the beam arm changed, and then returned to an identical state each time the arm went through a change of half a wavelength. By adjusting the length of our beam arms and counting the number of times the interference pattern cycled, we were able to calculate the wavelength of a We used this formula, where lambda, the wavelength of light, is equal to 2 times the distance that the beam arms moved, divided by n, the number of fringes that we counted. Our measurement resulted in an average wavelength of 666.67 nanometers with a variance of 82 nanometers, and a weighted mean wavelength of 586.03 nanometers with a variance of 8 nanometers. The second experiment used a similar setup to the first, except that a variable pressure chamber was added into one of the arms and used to calculate the refractive index of air. When the pressure inside the chamber was varied, effectively changing the length of the arm, the interference pattern changed as well. For reasonably low pressures, the refractive index of a gas varies linearly with the pressure. For a vacuum, where the pressure is 0, the refractive index is precisely 1. By counting the number of times the fringe pattern circled to an identical state, we were able to calculate the refractive index of air. We used the following formula, where delta n is the change in refractive index, delta p is the change in pressure, lambda naught is the wavelength of light in a vacuum, n was the number of fringes counted, d is the length of the chamber, and delta p is again the change in pressure. The data for refractive index versus pressure was graphed to find a line of best fit. Using the equation for the line of best fit and substituting x for the pressure at 1 atmosphere, our calculation returned a value of 1.000203 for the refractive index of air at 1 atmosphere, just 0.00009 away from the standard value. The purpose of experiment 3 was to measure the refractive index of glass by adjusting the angle of a glass plate in the path of one of the beams, effectively changing the length of glass that the beam travelled through. The glass plate was attached to a rotating pointer that allowed the changing angle to be measured. Once again, by counting the number of fringes in the interference pattern, we were able to determine the refractive index using the following formula, where Ng is the refractive index of glass, T is the thickness of the glass plate, and theta is the change in the angle. Our result in this experiment was not very close to the accepted value. The result of 1.001 compared to the accepted value of 1.5. This change was likely caused by the uncertainty in measuring the change in angle of plus or minus 1 degree. Changing the angle in our calculations by this amount caused a great change in the... In experiment 4, a completely different setup was used. We used a Fabry-Perot interferometer to measure the speed of light. Using the given values of the speed of light in a vacuum and the wavelength of the helium neon laser in a vacuum, the frequency of the helium neon laser was able to be found using this formula, where frequency f equals the speed of light c divided by the wavelength. By changing the distance between the two interferometer plates, we were able to measure the wavelength of light in air using a process similar to that used in experiment 1. Using the calculated frequency and the calculated wavelength of air, the speed of light in air was determined to be 3.078 by 10 to the 8 meters per second. Using our refractive index of air measured in experiment 2, we were able to calculate the speed of light in a vacuum, which was calculated to be 3.077 by 10 to the 8 meters per second, which is only 2.6% above the accepted value.
In retrospect, the use of interferometry has played a vital role in science and engineering, from initially providing one of the most accurate measurements of the speed of light to continue to play a vital role due to its usefulness in things such as LIGO in finding gravitational waves. Two experimental setups utilizing the specialized technique of interferometry were used. By observing interference patterns, we were successfully able to determine the wavelength of the HENE laser in air, the refractive index, and the speed of light in air and a vacuum, as well as unsuccessfully determining the refractive index of glass.